So what I am here to tell you about today is validation targets and what to do when you are trying to set limits with limited data. I want to provide some background to the remarks that I am going to share with you today. A number of years ago, the Technical Committee on Food Microbiology of ILSI North America partnered together with the American Peanut Council and convened an expert workshop. I have previously presented on the results of this expert workshop, but it was a few years ago, and actually at the time that I presented, the publication in the Journal of Food Protection had not yet been published. But in case you are interested, basically everything that I'm going to say to you today is distilled from information in this article. And you can see, maybe you can't see, but it is, well, it is Journal of Food Protection, volume 76, number 2, 2013. It is a general interest article, and that is the title of the article. And I do want to acknowledge all of my co-authors. I will also acknowledge them on a slide at the end. I also want to say that any of the mistakes I make or any of the nuances that I embellish upon are my own embellishments and not my colleagues. But the bulk of it was done by the folks that you see there on the slide. As a way of starting out, I want to share with you the questions that those of us who were active in the workshop were asked to consider. And so this lets you know the groundwork on which I'm going to build this presentation, and we are going to come back at the end of the presentation and have answers for you on these questions. So the first question that the people in the workshop were asked to consider: what are appropriate statistical and scientific methods for setting log reduction targets in the absence of pathogen prevalence and concentration, or with limited pathogen prevalence and concentration data? And I expect that this is probably, at least in many cases in the food industry, that is probably where you're going to be starting, right? You either are going to have virtually no information or only limited information. And that certainly was the case with peanuts a number of years ago, and that is why, in part, the American Peanut Council was involved in co-sponsoring this workshop. I'm pleased to say I had a conversation earlier in this meeting with Steve Calhoun from the American Peanut Council, and they've been very busy over the past few years collecting data. So of course, if you have limited data, you have to make decisions, you have to move forward. But one of your priorities should be to remedy that fact that you have limited data and go out and collect some data. Now, that takes time, that takes money. You need to assess the seasonality. There may be seasonal fluctuations for a given agricultural commodity over time, and it's very important that you capture that not only over a season, but over multiple seasons. The second question that the workshop participants were asked to address is: what constitutes enough data for determining appropriate log reduction targets for a given commodity? And again, specifically, we were asked some questions about raw peanuts. I'm going to try hard to not make this a talk about peanuts and almonds, but those are two products that I do have some experience in, and the examples that we can gain from what we've learned from those commodities, I think, can be very, very helpful. And then thirdly, I think, and this is a very interesting question, is a 5-log reduction in the absence of any data to establish a target log reduction science-based and appropriate? Okay? So if you don't know anything, can you just give it a 5-log reduction and then decide that that's, and if you can always decide to do that. The question is, if you do that, is that really science-based and is it appropriate? And again, we'll come back and we'll answer that question. What targeted log reduction would protect public health? So I think four very interesting questions, some multiple parts, which I hope to answer for you. As with many expert committees, the first thing that this committee did was to do something else besides answer the question. I can tell that some of you have served on expert committees. Well done. It's very rewarding and also just a little bit frustrating. I realize this slide is a little bit difficult to read. This is a table that is reproduced from the Journal of Food Protection article. And what I want to lay out for you, you know what I'm going to do? I'm going to take my glasses off so I can see the slide. Now you're all sort of a little more fuzzy now, but don't worry, we'll work through this. What this table shows is it's the importance of understanding the variability of your process. So we can say that, oh yes, we have a target 5 log reduction. But, and again, based on some of the things that you heard Nancy say, some of the time we may not have a 5 log reduction. For some particles or some entities moving through that process, we may have a 4 log reduction. Well, how you describe that variability ends up being quite important. So, again, let me walk you through this table. So what you can see in the left-hand column, and maybe, let's see, it looks like I don't have a pointer here. So I want to try to avoid turning around and using this pointer because my voice may go off the microphone. Oh, there was a pointer there. How about that? It just doesn't show up on my screen. Oh, here it is. Okay, so on the left-hand column, you see this is process number 1. And so in process number 1, we start off with the number of colony-forming units per batch, okay? And so in this particular case, and this is just particularly very arbitrary, right? We're assuming 10 million colony-forming units. Now again, as food microbiologists, we're all very comfortable working on a log scale, and that's great, and a lot of our processes are logarithmically oriented. As you begin to think about issues like this and understanding variability, and we'll get into it more in a few minutes about with cross-contamination, you have to be able to interconvert in your head or more likely in a spreadsheet between log CFU and CFU, and that is a very important thing to be able to do. So what you can see here is 7 different scenarios where you start off with 100 million bacteria, and then of course to show you that logarithmically, the next column is basically just that same number now converted to a log value. And then we apply to that, we apply a certain log reduction. Whoops, that was not what I wanted to do. Dangers of using, maybe I'm gonna risk losing my voice on the microphone. So here is the initial concentration. So here it is arithmetically, here it is logarithmically, and then we are going to say, well, what if we have really poor control over this particular process? And the variability in the process ranges from a 1 log reduction to a 7 log reduction. Nobody wants this in the real world, but this is important to think about. So we have this highly variable process. So again, you can just simply do the math. If you have 10 to the 7th and you do a 7 log reduction, you have 10 to the 0 at the end, that's 1 CFU, okay? So in the middle here, on the edges we have the CFUs, in the middle we have log CFUs. For that process, if you calculate the average log reduction of that process, it's just 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 7 divided by 7. And if you do that math, what you find is that the average of those numbers is 4. But look at what happens when you consider not the average log reduction, when you consider what actually happens to the CFUs. So here, look at the final CFUs. It's 1, 10, 100, 1,000 CFUs going all the way up. If you sum up all the CFUs at the beginning, which is now going to be 70 million, and you sum up all the CFUs at the end, and that's 1 million, 111,000, et cetera, and then you take the logarithms of those values, what you started off with was 7.85 log CFU, and what you end up with is 6.05 log CFU, so your effective log reduction is only 1.8. There's no magic here, right? This is just math. But what I want to point out to you is it matters whether you are considering these data on a logarithmic scale or an arithmetic scale. And so the point that I'm trying to make here with this long convoluted diagram and lots of circles and arrows is that in this particular case, we don't really care about the average log reduction. We care about the effective log reduction. And in this case, with a highly variable process, your effective log reduction is only 1.8. It's not 4. Okay? And that can be a big difference microbiologically. Now, the good news is that for processes that are less variable, and so here's an example where you have a much less variable. It's five different scenarios, and the log reduction varies between 3 and 5. Again, same math, same relationship. This is all in a spreadsheet. If you're interested, I can share the spreadsheet with you and do these simple calculations. The average log reduction in this case, where you have a less variable process, the average log reduction is 4, and the effective log reduction is 3.5. So that's good news, because that means that as you have a less variable process, the average log reduction more closely approximates the effective log reduction. But I want to point out that the effective log reduction is still less than the average log reduction. So bottom line, if you didn't understand any of that, the variability of your process is important, and understanding whether you're doing the calculations on a logarithmic scale or an arithmetic scale is important. Okay, the next little bit of math and spreadsheet that I want to demonstrate for you is the effect of recontamination. And again, this was another question that the expert committee chose to address because they thought it was important in getting to the point about what to do when you have limited data. So what this, and again, this is a little bit hard to read. It's a table taken directly from the manuscript. You can read the manuscript if you want to see it a little bit more clearly, but I'm going to walk you through it. So what we have is 3 different processes. We have a process that gives a 3 log reduction, we have a process that gives a 4 log reduction, that's in the middle, and a process that gives a 5 log reduction, that's over here on this side. So for the process where we have a 3 log reduction, we start with 1,000 kilograms of product, contaminated at 1 CFU per kilogram. So if you do the math, it's just 1,000 CFUs. What you end up with at the end of that is 999 kilograms that have 0 CFUs. Okay, that's not on a log scale, that's an arithmetic number. So 999 kilograms are bacteria-free. 1 kilogram contains 1 CFU. And so what you can do there is figure out you know, that's a 3 log reduction. And again, same thing for the next column. If you start off with 10,000 kilograms, you have 9,999 kilograms that are pathogen free. 1 kilogram still has a pathogen in it. And going over to the third column with the 5 log reduction, if you start off with 100,000 kilograms with 1 CFU per kilogram, you have, at the end of that, 99,999 kilograms that are pathogen-free and 1 kilogram that contains a pathogen. Well, what if, and so that's 3, 4, 5 log reduction. What if in each of those scenarios you recontaminated with 1 kilogram, in the first case, 1 kilogram containing 1 CFU. In the second scenario, it's 1 kilogram with 10 CFU, and in the third scenario, it's 1 kilogram with 100 CFU. So this is representing recontamination by progressively more contaminated, progressively greater amount of recontamination, right? So what you end up with then, in the first scenario, is 1,001 kilograms. And then you can, again, because you know the concentration of the contamination coming in, you can figure out the CFU per kilogram in that scenario. You basically count up the CFUs. Essentially, the bottom line in all of this is with that level, with a 3 log reduction and with that level of recontamination, you only end up with about a 2.7 log reduction. If you have a 4 log reduction and you recontaminate with 10 kilograms, so that's 10 kilograms coming back into 10,000 kilograms, you've taken that 4 log reduction and you've effectively turned it into a 3 log reduction. So again, about a 2.9 log reduction. In the third scenario, with a 5 log reduction, again, recontaminating now, taking 100 100,000 kilograms and recontaminating with, 100,000 kilograms recontaminating with 1 kilogram that's highly contaminated. I misspoke just a minute ago. Again, you're back to a 3-log reduction. So it's really important to think about recontamination and also the level of contamination coming in that fraction recontaminating. So bottom line, if you recontaminate, you're destroying the effectiveness of your log reduction. And again, the math in this simple table shows that. All right, so enough math. Let's talk words for a little bit. The first question. What are appropriate statistical and scientific methods for setting log reduction targets when you don't have good data on pathogen prevalence or concentration? Well, I'm here to tell you that there is no amount of science that is going to tell you what to do. Okay? Let me repeat that. There's no amount of science that is going to tell you what to do under those circumstances. If you have limited data, you're making decisions with limited data. The decision about the log reduction target to choose when you have limited data is a risk management decision. Now, I don't have time to give you a lecture on risk analysis and the difference between risk assessment and risk management, but let me just explain to you that risk assessment is a scientific process. Risk management is not a scientific process. It's a social and or political process about making decisions. So, of course, if you are going to make a risk management decision with limited data, yeah, it sure helps if you have an understanding of the science that underpins that limited data. It helps if you understand the statistics that underpin that data. And you should try to make a risk management decision that is scientifically defensible, but you have to deal with a variety of different factors. I mean, you have to deal with the individual risk-averse nature of the company. You have to deal with what it's going to cost and how long it's going to take to eventually plug the data gaps on those limited data. So it's not, there's no amount of science that's going to help you. It is a risk management decision. Now, that said, risk managers that have limited data can still commission risk assessments. They can still ask for a scientific assessment, but in the end, you are still going to be hampered by limited data. So that's, I realize, not a very happy thing to say. You were hoping maybe I was going to give you some magic answer with statistics that was going to save your bacon. But it's not going to happen. If you have limited data, you're just going to have to live with it. You should try to get more data, and you should try to make your decisions defensible, but science is not going to save you in that case. Related to that question, what are the appropriate methods, both statistical and scientific, for setting log reduction targets when you don't know too much about prevalence and concentration? Well, the bottom line is, with uncertainty, the solution is to increase the target log reduction. If you don't know too much, you're better off going with a higher log reduction. And that's what this little diagram is meant to represent. If that yellow line there represents the acceptable level of risk, and you don't know where you are over here with these with pathogen concentration, you are going to have to ensure that no matter what, you are at least meeting that level of risk reduction. And what that means is that you are probably going to end up over-processing some of your product to make sure that the most contaminated bit is adequately processed. Question number 2. What constitutes enough data for determining an appropriate log reduction? Well, enough data is once again not a scientific, there's not a scientific answer to that question. Enough data is a science-informed policy decision. How much is it going to cost you to collect more data? What are the consequences of over-processing right now? What do you know about the risks associated with that product? Do you currently have outbreaks? Is your best available information tell you you're controlling the risk with what you're doing right now? So again, no amount of science is going to help you out of that. It's ultimately a policy decision. The workshop discussion with regard to question 2, and Nancy touched on this a little bit in her comments, that what can we learn from related products? And if you have information, and in this particular case, the workshop was around peanuts, the models developed for other low moisture foods like almonds and pistachios could actually help to inform decisions related to peanut products. And so what I've done is I've sort of rewritten that in the next sentence, and that is to say that the risk framework, the data, the intervention technologies implemented in establishing log reduction targets for one product could be expected to inform and facilitate intervention targets for related products. Now, what do I mean by related? Well, again, that's probably a risk management decision. If you know something about one kind of nut product, it's going to probably help you with making decisions about other nut products. But again, what do we mean by related? Well, again, that's going to depend upon the specific context. In the interest of limited time, I'm going to skip over this particular diagram, but it just basically shows as you increase the log reduction, you get greater risk reduction. I do want to briefly show this. This is from a paper that I published with Michelle Daniluk and Linda Harris in 2006 on risk reduction for almonds. And the point that I really want to make here is that with the data that we had, we were able to express the uncertainty depending upon the chance that we would have a high contamination event versus a low contamination event. We calculated the probability, that is the percent of exceeding a certain number of cases per year if there was no treatment done on almonds, and then we took the same scenarios and the same chances of having more than one case a year, more than 10 or more than 100 cases a year, and then looked at what we would get from that with a 5 plus or minus a 1 log reduction. And what you can see is that the number of expected cases per year drops, but you still do have some finite probability of even having 1 case per year. Now, interestingly, that was looking at a 5 log reduction. What the Almond Board of California eventually netted out at was a 4 log reduction, and that was because of these science-informed policy discussions, not because of the science. Okay. Question number 3 is a 5 log reduction in the absence of any data to establish a target log reduction science-based and appropriate. Well, here I'm cribbing from Spinal Tap, a great movie. If you haven't seen it, that's highly recommended. This is Nigel Tufnell, one of the musicians in Spinal Tap, and Nigel was very proud of the fact that his amplifier went to 11. Okay, most amplifiers go to 10. Nigel's went to 11. Why? Why did it go to 11? 11 is 1 louder, right? So 5 log reduction is good, but 6 is 1 lower, right? And so you can always go for a higher log reduction. Does that make it safe? No, it just makes it proportionally more safe, just like Nigel's amplifier was proportionally more loud. So. The workshop participants were generally comfortable with the use of a 5 log reduction for controlling risk in products like peanuts, for example, even with limited data. So bottom line, food microbiologists, for a variety of reasons, some probably rational and some not rational, they're comfortable with a 5 log reduction. Okay, we're comfortable with 12D for Clostridium botulinum in canned foods. We're comfortable with 6 log reduction for certain meat products as specified by USDA FSIS. So, but you could do a lot worse than to do a 5 log reduction. But again, remember my comments earlier about the Almond Board of California in making a decision that 4 logs was appropriate. So again, that was a science-informed policy decision. It was not a scientific decision. Question number 4, what targeted log reduction would protect public health? Again, I know you're getting tired of hearing me say this, that is a science-informed societal decision. And again, I mentioned before about the work that we've done, that has done in collaboration with Michelle Daniluk and myself and others, looking at almond risk and the eventual decision to go with a 4 log reduction. So again, science-informed societal decision. So finally, where does that leave us? Well, that leaves me with acknowledging my co-authors of the report. You can see their names there. Also, I want to thank ILSI North America, not only for inviting me here today, but for inviting me to be part of that expert report so many years ago, and the American Peanut Council for their support as well. Thank you.
Time for a few questions for Don.
Good morning. I think that one way to address the things like uncertainty and variability of the process is working with design of experiments and randomization of the experiment to reduce the variability factor, and then enhance the efficiency of our resources. Through few experiments, we could reach good results with certain kind of trustness in them.
Yeah, certainly design of experiments helps when you're trying to figure out optimization of processes and things like that. Very often, however, in the case of these situations, there isn't an experimental design. You've just got to simply go out and do the survey work, going out into the field, going into the raw ingredient supply and testing literally thousands and thousands of samples to get a sense of what the prevalence and concentration is in the stream coming in. But yes, in terms of designing the process, there's a lot of advantages we can gain through design of experiments. Thanks.
Okay, thank you.
Don, thanks for the presentation.
You're welcome, Dave.
$64 question. The workshop participants felt comfortable with a 5-log reduction. I don't know how FSMA is going to play out or who's going to look at HACCP plans and say it's okay, but what's your view on putting that in the process validation plan and having it accepted by the inspector in the field?
I'd like to defer that question to the presentation that my colleague, Dr. Zink, is going to give later.
I would too. Great answer. Thank you.
I don't know, Dane. And again, as a guy who really is comfortable with numbers and who likes numbers, I sometimes just want to take my microbiologist colleagues' heads and smack them together and say, stop talking like that, you dummies. But sorry, folks. I don't know. I really don't know. It's going to be very interesting to see how it plays out.
And by the way, I'm comfortable with it too.
Thanks. You always referred to log reduction targets, and I didn't hear that you described or discussed how you verify that you've reached that target, given the difference between a lab protocol and in the real world. Can you talk a little bit about that? Because you can easily achieve a 5-log reduction if you set up your research in a certain way, and it won't necessarily have much to do with what you actually get.
Thanks, and thanks for that, Bob. So, and in fact, yes, and I know you and I have had many wonderful conversations about that one particular figure in Montville and Schaffner where we looked at seed disinfection technologies, and we discovered, according to the literature, that the more that you put on, the easier it is to achieve a certain log reduction. And so that is really important. I do want to say, again, and not in an attempt to evade it to answer your question, but there will be somebody else talking about evaluation of surrogates. And so I think, and what I'm pleased to see, from what I understand from talking with many of my industry colleagues, yes, you can do experiments in the laboratory with pathogens. You can't take the pathogens into the plant, but these, again, in the case of nuts, these roasters or whatever the technology is, these large pieces of equipment, we cannot use pathogens in even at maybe in a pilot plant scale if you have a BSL-3 pilot plant, but certainly not in the actual plant production environment. There's a lot of folks doing research with surrogates, and I think surrogates help us to figure out again, and if you got the right surrogate and you know how the surrogate behavior relates to the pathogen behavior, you can validate some of these large industrial processes, at least against the surrogates, and then if you know the surrogate's good, that gives you an answer. So that's part of the solution.
But even if you're using a surrogate, you can inoculate to a very high level.
Right, and this is really a very interesting dilemma, and certainly the effective inoculum size is something that we've been very interested in my lab for a number of years with respect to a number of different types of products and processes. And I still think, as microbiologists, we really don't have a good handle on that yet. And so part of the solution is to make sure that if you are doing experiments, is that you make sure that you're using good protocols, but also investigate the possibility of using different inoculum sizes. And if you use a lower inoculum, of course, if you use a lower inoculum, it's a lot harder to quantify that you've actually achieved, for example, a 5-log reduction.
I love this discussion. I have 7 more questions, but anyway.
Thanks, Bob.
I'm Dick Whiting from Exponent, and my name's up there, but I'm going to give not a minority opinion, but a little different spin on this.
Thanks.
And as Don was showing, with a typical process with contaminated ingredients, and you go through, and as you showed, assuming recontamination is not an issue, but generally a 1-log reduction will reduce the risk about 1 log. Mm-hmm. And a 2-log reduction will reduce the risk about 2 logs. And you think of our Healthy 2020 goals, you know, it's a 50% reduction. That's less than 1 log is our public health goals. So, you know, I kind of thought, well, and as a consultant now, I had one particular project with a process that was able to achieve a 3-log reduction without compromising the organoleptic quality of the product. You know, 3 logs. And so we felt quite comfortable. This was not a food that was known for creating a lot of illnesses. You get a 3-log reduction that reduces the risk 1,000-fold. I was quite happy in my omnipotent, consultant authority here to write that up and say, you've now got a safe product. And I think this is a very valid way to look at it, and I don't think the 5-log should really be, I say that, cast in stone, that is the standard.
Yeah, the only thing I would do is I would change one word in what you said from a safe product to a safer product. And in fact, how much safer is it? It's 3 logs safer, right? And would 4 logs be safer than that? Yes, but we have to decide what is safe enough. And safe enough, you're going to hate me for saying it again, safe enough is a risk management policy decision. But anyway, thank you for that comment, Dick.